advisor in this like style.
The branding people keep changing the templates, you know, every now and then, and like every time they change it, like all the colors get messed up.
I see. This looks nice for presentation.
And yeah, like sometimes depending on like how strong the projector is, sometimes it ends up too dark and something like that. So
I think your mic is turned on.
yeah, it's all muted at the moment.
Okay.
No. We all know that. Yeah, it's always too much complicated. It's too complicated getting that set up. Too loud, too quiet. Modulated. Makes the file like 600 megs.
The question is cartoons about computer architecture.
I've got some cool stuff, but it's not videos. So how would you
Animation.
Front end or
Okay.
okay, sorry. Then the question. And technically, at some point, I still need to actually sign there's some like video release form I'm supposed to sign. So I'll sign it so we can effectively execute it and we'll commit that far. Someone will probably want that. I imagine that someone people at some point right.
We'll see, but it's good to get all the different content.
Yeah. I want to see silicon.
We typically also start like 10 minutes after the hour.
Yeah.
For daytime things still.
Yeah, people have to get from building to building.
We have 3 buildings, so yeah. So typically either in this room or in the other room.
That is interesting. Sometimes you get the teaching assignments in classrooms at the other end of the campus.
Oh, really? That happens?
Oh yeah, I have sometimes like they end like I'm running the class or like sweaty and
Interesting. When I visited they were telling me that it's very important to get the parking permits. It's something that's very like you need to actually get it close to your office.
And you have to pay for it.
It's the same here. We also pay for
state score.
My first semester I got like 3 or 4 parking tickets.
Can you just start?
No, unfortunately.
Why not?
Yeah. So eventually I figured out where I should park my car.
Also like Atlanta, especially. You look at just like 20 minutes, right? Like you're just raining like crazy for like 20 minutes. It's like ready to go home, and like you're gonna walk your car, and it starts raining. Like, okay. But you wait like 20 minutes, 30 minutes. So it's like
is that the entire year or like more seasonal thing?
it's probably more seasonal, but yeah, parts of the year where just after you just before. So that's part of the problem of having the
Maybe that's the reason. Yeah.
having the right parking lots. It's like because the first year I actually had outdoor parking. Right? So that's the problem. We moved to a new building. They had parking underneath. Right? So there was a lot easier to deal with. Different people, easier things. After you get first day, right?
Why in a big department you didn't get the first pick? Well, we're very excited. I mentioned these 2 buildings. The department will grow and we have space. A lot of interest, a lot of activity. Well, when we actually walk through the dinner, we actually pass some of the structures. Like some parts of it.
And you don't have any indication. Then you just have like
Whatever you want. So then do we also go until 5 after or we stop at the hour?
It's better to at least save 5 minutes for questions. Yeah, I think we would be so 5:10 will be the hard stop for another discussion, but we do have this 10 minutes buffer. Yeah, so it's up to you. But I think they like to have all the questions saved to the end, so it goes to your
Okay.
and that will
Okay, so
okay, I think that should be fine. We'll see.
Maybe they even have like if they're doing short.
Okay. Hello, everyone. Are we streaming already? Okay, good. Well, good afternoon, everyone. I'm Sophia Xiao. I'm a faculty member here at the EECS department. It's our great honor to have Dr. Gabe Low joining us. Gabe currently is a senior fellow at AMD and has a very distinguished career. Before AMD, Gabe was a 10-year faculty member at Georgia Tech, and he has won a lot of awards, including the ACM Maurice Wilkes Award and Hall of Fame for a range of leading architecture conferences. On top of that, Gabe is also one of the best hockey players in computer architecture community. Before the pandemic, one thing I always look for is email from Gabe in organizing architecture hockey game during ESCA. So that's fun, and I'm looking forward to the return of the game after the pandemic. So with that, Gabe will share with us some of the interesting efforts from AMD in really thinking about future generation technology scaling and 3D integration. And Gabe will share us with his thought on silicon cityscapes. So
Great.
Gabe, take it away.
Thank you very much. And yeah, the bar for being a good hockey player in a computer architecture community is not very high. So before we get started, just kind of a quick, just so I kind of understand the audience here. How many folks here are more, classify themselves as kind of computer sciencey by show of hands? Okay, and then I'll assume by subtraction, the rest of you all are more, electrical engineering, ECE minded. Okay. How many are faculty? Okay. How many are master's or PhD students? And do we have any brave undergrads in the crowd? Awesome. Okay. I wish I had I should have brought some candy bars to hand out. It's almost Halloween here. Okay. Good. Okay. That's just so I can kind of calibrate and make sure I, know your audience. Okay, so today I'm going to talk about Silicon Cityscapes, which is kind of just a fanciful, kind of playful name for kind of this kind of concepts and such we're going to talk about. I'm heavy into usage of analogies and such. Sometimes analogies work well, sometimes they're a little forced, but bear with me. So tell a little story about kind of the development of humankind on this planet and how we've progressed and grown over time, and in particular how we've evolved. How we live and work, and use that, to draw analogies to, what we're doing in the semiconductor space, and perhaps hopefully get some insights as to where things may be going in the future as well. Okay, so we'll start back, looking, where we've come from, right? And so, people in general have been, on this Moore's law curve of sorts for some time, right? And actually, it's a log y-axis, and even a couple centuries ago, the base of the exponent changed a bit drastically as well. And kind of the analogy on the silicon side is, kind of whether you're counting devices or performance or capabilities, right? We've kind of gotten spoiled a bit in this industry with this exponential increase in capabilities, right? And one thing is just over time, as those capabilities increase, we've had to change, how we live or how we build our, our dwellings, our villages and cities, and we've likewise had to do, evolve our computer architectures to meet these new capabilities as well. All right. This is just kind of a Wikipedia picture I found of San Francisco in 1855. Back when you didn't have a lot of people, you could do things a little bit more simpler and such. But as the population increases, the architecture evolves, and you have something that looks like this today, or whenever this picture was actually taken, might not have been this year or not. And again, the kind of underlying theme is that the architectures, the approaches change, right? And very similarly, if you go back in history with silicon chips, back in the day, things were a lot simpler. You had tens of thousands of devices, perhaps a couple tens of square millimeters of silicon. This is something back then people did layout by hand, right? You can actually just literally people print stuff out and put it out on the floor. You can debug things that way. And these days we're now talking billions of transistors, right? This isn't even drawn to scale, right? And again, this poses certain challenges to what we do. One of the things though is it's not just we're scaling these devices to have more and more transistors, right? But we're also this is happening in the human space, right? We kind of are starting to run out of real estate, right? You look at the Bay Area, you've got San Francisco here, and you've kind of filled in all of the space. You can't really grow anymore. And one of the things we've been seeing in the silicon space is also we've been growing the sizes of the chips over time, right? So it's not just that we get more devices per square millimeter, but we're also spending more total square millimeters to build larger and larger chips to deliver more capabilities. And we're now getting up to this point where we've basically hit the reticle limit, right? Which is the maximum area that you can do your photolithography on to basically print the chip. Right, and there are people looking at doing multi-reticle things and stuff, but that it becomes grossly expensive to do those things. And this is up near that 800 square millimeter mark, right? So we've in a lot of these situations are kind of running into this this problem of the Bay Area, right? Like you've run out of room to expand. And it's not just that, but it's also, the silicon itself is becoming more and more expensive, right? So this is just some open data I was able to find actually from Singapore. I had the fortune to visit Singapore a couple of times this year. And I think if you found a chart for the Bay Area, you'd probably see some similar types of curves, right? Just the cost, per square foot, keeps going up. Right, and frighteningly, we're kind of seeing this same trend in the silicon space as well. Right, traditionally, you go back, in time. One of the powers of Moore's law was almost more of an economic factor. Right, every generation, it wasn't so much you got twice the density, but you got twice the devices for roughly the same cost. Right, and that allows us, as consumers, we kind of got used to the fact that the cost of a laptop, the cost of a computer, whatever, roughly speaking, has been constant-ish over time, but the capabilities keep getting better and better and better, right? We're now hitting this point though, as we get to these later, the cutting-edge silicon technologies, that the cost, for the same amount of silicon is actually increasing at this, somewhat alarming rate, right? So I can get more transistors per square millimeter, but per square millimeter I have to pay more dollars. And so that also introduces a lot of interesting decisions, right? Because at the end of the day, I can architect my processors in a certain fashion, but there are cost implications to that. Analogously, I can build all different types of buildings, right? But the type of building architecture I choose, it depends what kind of budget I've got to spend on that. Oh, there we go. So this kind of sets a little bit of backdrop of kind of where we are, some of the current, and these are the challenges as of today already, right? So this next section I want to talk a little bit about what are we doing currently to try to address some of these issues. What are the current approaches to this? Okay, so we just had this chart showing that the cost of the silicon is increasing. What's also perhaps a little bit frightening is that if you then combine this with the previous chart on the kind of the sizes of chips over time, is that the first chart is actually just showing the rough cost for a 250 millimeter square chip, right? Was actually down there here, right? And then one of the other challenges though is that the cost of silicon is actually nonlinear with respect to the die size, right? As if you have a chip that's twice the size of another one, it can easily cost much more than twice as much, right? And the easy way to think about this is that when you manufacture a wafer with a bunch of chips on it, the bigger the chip is, if something goes wrong, right, you have a manufacturing defect, the larger piece of silicon you have to throw away, which means everything else has to, you have to charge the customer more on everything else to make up for that cost, right? Or if I manufacture 10 cars, I have to throw away half of them, I need to charge everyone else twice as much per car, right? And so there's this challenge, right? It's this very nonlinear type of effect, right? So if you're looking at the first chart where the price per square millimeter of silicon is increasing, and then you combine it with the second chart where now we have to trying to build these gigantic chips that are now scaling in cost in a super linear fashion, right? That puts it into a very difficult situation, right? We want to deliver that additional performance, the additional capabilities to the end users, but this is not economically viable. So one of the things we've, AMD, has been pushing this, and other folks have been talking about this quite a lot, is kind of going the other way, taking advantage of that superlinear curve, right? So if I've got 4 families to house, right? Like I might not want to build like a giant McMansion to to house them all, and instead what we do is we build perhaps and that's kind of like a single monolithic chip. What we do is we build neighborhoods of smaller houses, smaller units, right? Because on a per house basis, it's actually cheaper and easier to build that, right? And the houses probably don't have the same superlinear scaling as strongly as silicon does, but the concept's kind of similar, right? So by taking some amount of total silicon capability, right, and if we can partition that into smaller pieces, we can basically ride that superlinear curve in the opposite direction, right? So if I can break it into smaller pieces, if each of these pieces perhaps roughly a quarter of the size of that original silicon, each piece can actually be far less than 25% of the cost, right? Because of that reverse superlinear trend. And so this was actually something that we kind of the concept is pretty simple, right? So you can basically take your silicon wafer. From that, you're going to make a bunch of these chips. Sometimes people call them chiplets because it's kind of a a smaller physical piece of what logically would be your overall functional chip. And kind of as I alluded to earlier, manufacturing isn't perfect, right? So some subset of these are maybe faulty, right? And what happens, each one of these is faulty. I'm now only throwing away like a quarter of the silicon compared to the previous case if I try to build a single monolithic chip. Right? Once I've done this testing, I throw them away. I can take the remaining good parts and then package them up, and now I've got a bunch of functional products that I can sell, right? And then this provides a much higher amount of yielded processors versus if I try to build this as a single monolithic design. Right, so fairly straightforward process, and the concept of multi-chip modules is not new, right? This has been around for decades in various forms, but hasn't really been used a ton in the kind of the commercial space, largely because there is some additional cost that does come with having to reintegrate all of these pieces together, and I'll talk about some of those soon. Right, and so we actually first deployed this in our first generation EPIC processors. These are basically our CPUs aimed at kind of the server space, right? And this is going back to some times that perhaps our marketing PR folks would prefer me not to talk so much about. But things were a little bit rougher for AMD back then. We were trying to get back into the server space, and from the folks who are doing the product planning and the market research and whatever, basically came up with a set of requirements that said if we really want to get back into the server space, have a competitive product, and kind of our first generation part had to have the capability to scale up to 32 cores, right? We needed something to differentiate. They decided we had to have support for 8 channels of memory. Kind of the competitive parts at the time were 6, so that's a 33% increase in your memory bandwidth per socket. And also, the other thing that they targeted is we want to provide a lot of, I/O, right? So 128 lanes, which is, again, a lot more than it was provided. The numbers here, don't need to worry about so much. But the main challenge was that if we were to, take a traditional approach of building a single chip that had all of these, capabilities, this would be, getting close up to that reticle limit, right? It's 777 square millimeters of silicon. This is back in a 14 nanometer node. And the problem then is just this is so big, it would not have been cost competitive, right? Yes, it would have all of the features and capabilities that we wanted to, but we'd have to charge some really high price so that we could actually not lose money per part. That at that point it would no longer be competitive, right? So it was just it's what we wanted, but we couldn't build it. So the approach then in some sense we did chiplets. Why did we do chiplets? Well, because we really had no choice. Right, it was kind of like the only viable solution, right? So what we did is we build these smaller components, which unsurprisingly each have a quarter of the capabilities. 8 cores, 2 channels of memory, and 32 lanes of PCIe. And each of these ends up being roughly 213 square millimeters. And so the cost is significantly improved because of that that superlinear cost per area curve. What's kind of interesting though is that if you actually add up the total silicon, it's actually more total silicon than that monolithic design, right? That monolithic was just shy of 800 square millimeters. We're actually, shipping 10% more silicon per processor, product from this. I can't show you all the math and models and such, but basically, our estimate was that this still comes out at roughly 60% of the cost of compared to if you actually built a single monolithic chip, right? So that's just kind of the power of that superlinear curve that you can write it down the other way. And it's not for free, as I said, that there's that 10% kind of extra total silicon because you need to have extra interfaces for one die to talk to the other. There's other replicated resources, just kind of like power management, clocking, and other basic test features that you have to replicate on a per die, per chip basis. But overall, it still put us into a position where it's like, hey, now we can actually deliver that full list, that full wish list that the marketing folks had specified for us, while keeping the finance folks happy and that we can make a profit off of these parts. Right, so that's kind of like our first approach to kind of this chiplet journey. So what's kind of interesting is that you look forward, you think about the different functions of the chip. Different just like in real life, different things that we do, different jobs and whatnot, we do in different types of buildings that are architected differently, right? So like this is a picture of like a luxury mall, right? And in a mall you have marble and glass and all kinds of fancy materials, and that makes sense because you've got a bunch of expensive shops that go with it that people pay high rent and it all works, and that makes it's fine, right? So that kind of architecture kind of approach makes sense for that use case. Right, this is a photo I found of a parking lot from the Indianapolis airport. Right, you wouldn't go and deck this out with all kinds of fancy metals and all the marble on ramps and things of that sort. Right, because it doesn't fit the function of what you're trying to accomplish there. Right, and one of the things that we're seeing with the silicon is that we're actually seeing this this diversification in terms of like what types of silicon, what types of technology is suitable for what types of functions. And so that's actually one of the drivers for our second generation of chiplet architectures. Right, so this is actually a view of our first generation chip. And what's highlighted here is the core logic areas, right? So it's 8 cores plus the L3 caches. Everything else, for the most part, in a darker area consists of things like your analog components for your I/O interfaces, your memory controllers, and things of that sort. And so the challenge is that, in theory, when we went from 14 nanometer to 7 nanometer, our estimates was that you can get about a doubling of device density, right? It's not quite as good as it used to be, where that really should have been like a 4x back in traditional Moore's law days. But the challenge is that doubling density only applies to kind of the core logic components, right? And so ideally the chip should be 50% of the size, but only half of this, roughly half of the chip is actually going to benefit from that shrinkage, right? And so you're only going to get like a 30% reduction in the chip size. And then when you combine that with the fact that going from like 14 nanometer to 7 nanometer is like, it's a little shy of a 2x cost adder, right? You're going to be behind, right? Because this is just for the chip as is, right? So I'm not delivering, any more cores or a larger cache or anything. This is the same core, the same cache as the previous generation, but now I'm going to actually pay more for that, right? So like that doesn't make sense, right? So the challenge here, of course, is that, well, if some of this logic, right? Again, I guess kind of the I/O and DDR, you can, analogous is maybe more like your parking lot side of things. Probably the people that work on that may not appreciate being characterized that way. So it's again, the analogies aren't perfect, and anyone who's done analog design knows that it's actually quite challenging. But we can basically take the same type of approach, the same type of philosophy. So well, if something wants to use or benefits from that more expensive technology, then use it there. If something doesn't, well then don't use it there. So our second generation approach to building our EPIC processors, introduced the heterogeneous mixing of silicon technologies. All right, so we have this central what we call the I/O die and these CPU chiplets. Okay, so each of these, the main I/O die, we kept in a more mature process. It's more cost effective, and again, like a lot of these components, weren't going to benefit from scaling to 7 nanometers, so don't do it. And that makes that part much more cost effective. And then each of these CPU chiplets we could then implement in this more expensive technology, but it's where you're actually going to get that benefit. Get the better transistors, better power efficiency, right? Where that cost does pay for itself in terms of end user value. And you can see in this in the layout that this chiplet now about 86% of the area is made out of the components that do benefit, right? We still have some overhead. Even your big fancy mall, you have to spend some space on bathrooms and storage areas and things of that sort, right? There's some overhead. You can't make it 100%, right? But this is a huge change from the trying to take our previous design as is and just shoving it into the new technology, right? And again, these are things where, at some level from a technology innovation perspective, like, yeah, we always want to do the new things, the cool things, right? But from like a product perspective, from a commercial perspective, if you don't have to do something, you don't really want to do it either, right? And again, like this is sort of forced just because of the changing economics of the silicon, right? The fact that the new technology was that expensive, we couldn't afford to just do things in the same old fashion. Okay, so and we sort of seen this as kind of this, generational, evolution of our processing architectures, right? And sort of, we've gone from the old, traditional monolithic, single, big house approach to, kind of make these a small clustered neighborhood approach to now, this is a little bit more like, having like a little town square, right? Where you have a lot of the common, public space, the shared resources, and perhaps water fountains and such in the case of a real town. In this case, you've got your shared I/O and memory controllers and whatnot, and then you've got an array of these other components around it where you can sink more of your engineering and cost or whatever into building up nicer homes without having to completely make the town square just ridiculously blinged out. This is not Las Vegas, right? So that's kind of one dimension of how we've been breaking things apart, and part of this also once you cut things into smaller pieces, they still need to talk to each other and have interconnects, right? So for a lot of the earlier generation parts, we actually just have it's still this very like planar 2D type of array, right? We've broken things to smaller pieces, but they're all sitting next to each other in this 2D fashion, and that's okay when you have enough space, right? So kind of, a city like LA, you've got a lot of, square mileage, and as a result, the city over time has just kind of sprawled out, quite a bit. But there's other places where you're space constrained, right? And in that case, what ends up inevitably happening is you run out of space, but you still have to provide more capacity, right? You start building up, you start going vertical. And the silicon industry has been doing that in certain areas already, right? And again, like you don't want to build a skyscraper if you don't need to, right? Like, if you're Costco and you just build a big, one-story, facility, that's fine. But actually, I had three skyscraper Costco sounds kind of scary anyway. But in other cases, like, that's the way you go. And so, we've been doing this in a variety of forms, all right? So in some cases, you don't have to build, it's not like you just build either a single story building or a skyscraper. There's also intermediate levels, right? So what we've started doing in some of our CPU parts is, doing just a two-level building, right? Fairly, it's easier to manage, easier to, construct and handle the engineering with, right? You don't go straight to building skyscrapers after you've mastered building, wooden huts. And what we've done is basically in this case taken our existing CPU processor die and stacked additional SRAM on it, right? So this allows us to build a much larger L3 cache for this. Architecturally, perhaps a lot of folks find it maybe kind of uninteresting. Like if you do performance simulation, it's just changing a knob from the L3 size from X to 3X. But there's actually a lot of engineering involved in making this work. There's a lot of kind of floor planning and power delivery related things to make sure that this all works. This is also designed to be modular, right? And that majority of our products don't require this additional cache, right? So we can actually sell that bottom die as your traditional regular sized L3. as is for a lot of the markets. And for the ones that do want the extra cash, some of the highest end gaming PCs, or some of these very high end data center and HPC type of facilities do have workloads that do benefit tremendously from this extra cache. So one of the kind of neat things here, which kind of breaks down the city analogy a bit, is that it's actually optional, right? And then that's not the only thing that's been done, right? On the memory side of the world, they've actually been doing die stacking perhaps earlier and more aggressively. They perhaps look a little bit more like the skyscrapers of sorts, right? HBM stands for high bandwidth memory. It's a JEDEC standard memory. AMD's actually been shipping GPUs with HBM since 2015, right? And they're building early days 4 high stacks, and 8 high stacks are the norm now. But again, it's for similar reasons, just like kind of in the real estate type of perspective. Like you have only so much space, and you want to get as much in this case memory capacity as possible in there. So you start going vertical, because trying to build a gigantic, and they're having the same problems that we have on the processor side, right? If they build a gigantic die with all the DRAM on it, they've got yield problems, cost problems. Their equations are a little bit differently, because the DRAM is regular enough that they can do some more harvesting and repair compared to like your random logic and your ALU. But even so, that at some point you build it too large, and enough things fail, you can't repair it. You have to throw it out, and that becomes too expensive. So there's similar benefits for them to do this too. Another kind of related technology that both AMD and others in the industry have been looking at and making use of is this weirdly named 2.5D integration. It's physically doesn't really make sense as far. I never took a sufficiently advanced physics class where we had non-integer dimensions. But I don't know. The physicists sometimes have some interesting things, so I don't know if it exists or not. Right, but one of the challenges for especially something like memory is that traditionally your memory is outside of the processor package, which means your bandwidth to it is going to be limited by how many pins and interconnects you can have from the package out to the memory chips, right? And analogously, that's sort of like if you actually have like all of your residential parts of where people live, geographically segregated from like the commercial business areas of town, right? That then basically ends up having longer commutes, more time spent commuting, more energy spent commuting, right? It's as you don't have the adequate bandwidth to get from where people live to where they want to work. And so the notion of this kind of 2.5D type of integration is it's fairly simple, right? It's like, well, we can stack this memory up, get them more compact, and then basically integrate it directly into the package itself, right? And there's a couple different technologies for how you tie these things all together, right? But then the end goal is to try to get more towards these these newfangled mixed use type of developments, right? Where you work, live, and play in the same place, which means you spend less time, less energy trying to get from point A to point B, and more time doing the stuff that you want to do or that you need to do. Right, and so again, same thing here, right? We can get things together. That's it's whether it's dollars, whether it's joules, or whether it's actual time. That's all time not spent on data movement. That's time spent on compute and getting to your solution, whatever it is you're working on, faster. So in terms of how this is actually done, there's a couple different technologies out there. Silicon interposers is kind of the earliest one. A silicon interposer is really just a big piece of silicon where we didn't bother making any transistors, right? So we just put the metal layers on top, and we can connect the chips on top. So this is where that 2.5D like name comes from, because it's technically 3D stacking. You're 3D stacking your chips on top of this silicon interposer, but the chips that actually matter, like your memory and the processor, they're kind of stacked 2D with relation to each other, right? So I guess that's probably the motivation for why they originally came up with this term 2.5D, right? And so that silicon interposer, is but it is fundamentally still a 3D stacking technology. They actually have to implement what they call through silicon vias, which is metal interconnections that punch through that silicon, because that's how you actually escape out your I/O. That's how the power and ground is hooked up from the bottom of the package substrate. More recently, folks have been making use of different silicon bridge technologies. So one of the challenges of the silicon interposer is that whatever I'm stacking, I need to have an interposer that basically is the size of the bounding box around everything I'm stacking, right? So, and that can become quite large. And even though there's no devices on it, it's still silicon. You still have to do the TSV manufacturing. You have to thin the die. There's still considerable expense that goes with that. And so what many folks have been looking at more recently is these different silicon bridge technologies. So the AMD version is called this elevated fan-out bridge. There's another version which is an embedded bridge, where basically instead of building this giant interposer, you just build this tiny little piece here. It's just like a little underpass, right? Connecting the two adjacent buildings. Right, and that's a lot easier and cheaper to build. You still have to have some interconnects, other copper pillar type of connections between. Right, and then the other technologies is you kind of delete this layer, and then the bridges go down in the substrate, which is an embedded bridge, right? But I mean, topologically, they're all pretty similar. They all accomplish the same goal of providing that lateral chip-to-chip interconnect with high density. Okay, so that's kind of like where we are today, right? That's a lot of just the current technologies and how we've been addressing these issues of costs, of running up against the reticle limits, and how we're scaling the systems to build what already exists. So kind of in the remaining, call it 20 minutes or so, I want to talk about okay, where are things going to go in the future, right? So this is this section is actually going to have very few answers. The objective here is hopefully that this may encourage or inspire some new research problems for folks to look at and think about. This is another area where even though my background's computer architecture, hopefully a lot of these problems will inspire some thinking across the stacks, taking ideas and approaches from other areas of ECE and computer science, because I think a lot of the problems are fairly kind of foundational. There's just kind of algorithmic approaches to things, and a wide variety of problems where our colleagues have been thinking about these things perhaps in a slightly different context, but have great expertise and may provide insights for us. Okay, so kind of the trend is we've got this continuing performance demand, right? The demand's not slowing down. Anyone who's attended any sort of AI talk has seen the charts of natural language parameter growth rates and things of that sort, and the amount of compute needed. But it's not just AI, even though they seem to pay a lot of people's bills these days. But just all across the board, right? Like the demand for compute is not slowing down. We do have these constraints of these increasing costs of construction, right? This is again similar to the real world with recent inflation and whatnot. And then we also have these physical form factor constraints. So, you can't necessarily build these things to be significantly larger. So if you consider that, and then simultaneously we're hitting this point where it's kind of exciting, where we're really seeing the maturation of a lot of these new advanced packaging and integration technologies, right? So we have the demand, we've got these capabilities, and so I think it's like the right time to start thinking about okay, well, what's going to come next? How are we going to start combining all of these things together to address specific applications, specific use cases, right? And I think it's a wide open space, horribly multidimensional. But I think there's a lot of rich questions to start thinking about, start asking. And so kind of the next couple slides, I'll start talking through what some of these issues, what some of these challenges are. And some of these are things that hopefully folks are already familiar with, but there may be some new twists, new extremes as we integrate things together. I'll just talk very briefly because this is a term that's come up a lot in if you're out there reading papers or listening to other technical outlets. There's a lot of buzz around what people call heterogeneous integration, right? And there's some overlap between heterogeneous integration and kind of like what we're pitching as this vision of these silicon cityscapes of the future. But really the heterogeneous integration is really looking at a lot of these fundamental technologies that are all necessary for building these future systems, right? But from my perspective, there's a lot of I think at least for my research interest, there's a lot of questions. Okay, assuming that heterogeneous integration is successful, they work out these technologies, we know how to build all these things. what is it that we should be building, right? Like, how do we actually go about architecting things, right? I don't want to, it's certainly important, but like I'm less interested in finding new mixtures of concrete that are sufficiently strong but are lighter or whatever. And I want to think about like what are the buildings that we should be building with these new materials, these new capabilities. And there's some parts of heterogeneous integration that also don't overlap. There's some additional focus on like IoT and supply chain and materials and things of that sort, right? So I think they're complementary. There are some areas of overlap, but I think there's especially for kind of those with the architecture mindset, there's a little bit of a different focus, different set of research questions to be looked at. Right, so they're not competing. There's enough work for all of us to do. So kind of a first question is like what kind of city should we be building, right? And so if you look at real world cities, the different cities that have different functions tend to end up with different type of architectures, different type of planning, right? Like a port city has a particular type of infrastructure set up, if you're manufacturing centric, again, like there's maybe have like railroads or other things to bring materials in. You've got different kind of planning for how the workforce is going to be housed and such. College towns are another like it's a lot of transient population. You're going to organize things in a little different fashion, right? But ultimately, cities are built for people for certain purposes, all right? And so the Silicon Cityscapes, I think, are likely, going to follow suit, right? Like, well, what is it you're trying to build? What problem are you trying to solve? Who's going to, buy and use this particular product, right? And in each of these cases, that particular use case is going to drive what type of a, silicon solution you're going to want to architect, right? And each of these will then drive what kinds of processing elements you have, what kinds of memory, what kind of interfaces, so on and so forth, right? So I think fundamentally you need to start with like why am I even building this, right? Not can I build it, but like what's the purpose, right? Kind of the next component, and this is kind of in some sense more kind of classic architecture, is that you're going to have different types of buildings to populate the city with, right? And this basically the analogy is just your different processing components, right? So this could be your CPUs, your GPUs, an entire bevy of different domain-specific architectures that folks here may be developing, right? It's just like what are the different buildings? Again, it goes back to that previous theme of like what are you trying to accomplish, right? Like I don't want to. If I'm looking for a place to live, I don't want to be constructing that that thing in the middle, right? And so there's a lot of continued I think a lot of these things are complementary, but definitely I think at times from a research community we sometimes just kind of go after like the newest shiny object, right? And just this kind of reminder that the fundamental compute is still absolutely important, right? Whether it's a CPU, a GPU, other forms of accelerators, we need to keep pushing on that. And there's obviously a ton of great work happening here on a lot of those fronts, right? So don't slow that down. Another kind of interesting aspect is that kind of underlying a lot of this stuff is cost, right? There's a human cost to a lot of these things. There's material costs, verification costs, all kinds of things. Right? And we also see this in the way we do real world type of stuff, right? And sometimes we view it as more of an eyesore, cookie cutter townhouses and things of that sort, right? But those are valuable in if you're the real estate developer, right? You design one house and you just stamp out a whole neighborhood's worth of them, and so long as people are willing to buy them, you make more money that way, right? On the other end, you can do fully customized bespoke solutions as well. Right. This is I live in Seattle, so this the Frank Gehry structure there. I'm actually not a big Frank Gehry fan but it's I think a good example of something highly customized with zero reuse as far as I know, right? And this is something that we also depending on the function and what it is you're trying to accomplish, we also take advantage of this at AMD. Right, so for example, our CPU chiplets, we actually make use of in the server parts as well as in our commercial kind of client consumer parts. Right, the desktop or laptops you have, they just use a smaller number of these chiplets because I don't need 64 cores in my laptop, but I can have that same silicon reused in multiple places, which then has these economical and engineering effort type of benefits. In other situations, we actually have to go in there and do much more customized designs, right? So with a bunch of our game console customers, right, we do the silicon for the Xbox and the PlayStation. We work closely hand in hand with them and actually, do what we call a semi-custom design, specifically for their platform to meet their needs, right? So there is this range, and again, a lot of it just comes back down to the economics of it. Like, is someone willing to pay for it? And they're willing to pay enough for it to justify the effort to do something specialized? Or in other cases, can I get away with something that's a little bit more regular that I can reuse in multiple places, right? And there's not one's better than the other. It's just, I think, for each of these, sort of, silicon cities that one might want to create, you have to figure out what makes sense for your application, for your target constraints. To go along with this, right, we have all these different components, all these different buildings. You need infrastructure, right? And this is a part where, sometimes it seems a little bit unglamorous, but actually, requires quite a lot of engineering, a lot of planning. These different components, there's lots of different ways we can hook them up, right? There are some components that need, tons of bandwidth between them. I might need like some, the equivalent of a mega highway in there, right? I can have, tons of bandwidth to get from point A to point B. There's other places where I may have, really urgent, type of traffic, high priority traffic, and I need, dedicated, maybe HOV lanes or something of that sort, where, it's, things that are, on the critical path of execution, things for like, synchronization, communications or things of that sort. In other cases, for the types of, I have so much data that I need to move, I really need to be energy efficient, right? And so maybe I give up a little bit on, the latency and other aspects, right? So you end up taking, BART or something like that, right? It's, it can move a lot of people, but you may be waiting around at the station for a while before the next train shows up, right? But in aggregate, at least, I won't comment on BART specifically, but, the public transit systems, in general should be providing like kind of a more, efficient total, transport solution, even if individuals, aren't happy with their delivered service. Right, but again, if I'm talking about the total amount of energy I have to spend in this chip, I'm doing this large machine learning training or something like that, that may indeed be a critical aspect. And so as we think about these different combinations of these different chiplets and 3D stacks and such, there's a lot of, I think, challenging work to figure out like how do we actually go about architecting the correct infrastructure to tie this all together in a scalable fashion, in an efficient fashion. I know there's some work going on here in trying to automate the process of generating a network on chip and things of that sort. What are the challenges when you now have these additional chiplet to chiplet constraints and other application-driven constraints at the same time? How do I generalize this in a way that meets the needs of the city while not being you have to be able to verify it and make sure it really works, right? Kind of the other sad real-world comparison is that we build these things and it takes us 12 years to add 3 stations or whatever, right? It has to be tractable to construct. And I don't know the answer how we do that. So hopefully, I'll see some interesting papers in the next year or two giving us some answers. We talked about real estate a bit. Earlier we talked about kind of the chip real estate, right? In terms of we can't build the chips any larger, they're reaching the reticle limits. We actually have a similar problem or challenge with the packages themselves, right? That, the package, there's some physical size of a package, and yes, technically you could build a bigger package, but again, it becomes more expensive, it becomes mechanically more difficult to build something that's, that reliable. There's a whole other, set of folks that worry about, things like package warpage and how that, puts stress on connections and things can break and whatnot. And just the bigger it is, the harder it is to construct. And so we're, running into these bounds where we want to stuff more in there, but we can't. Right. At the same time, we've got these different use cases that we care about. So when you think about what you're going to have to put together, we're going to have to come up with some very different cityscape type of architectures in the future, right? Because we're just getting boxed in from so many different sides, right? And the technology is getting more challenging. Right, so as we think about a given application and how we compose things together, we actually have to think and this is where I think a lot of the thinking has to go more and more across the stack. Right, I have to figure out like how do I partition my problem, my logic across the different chips, and then how do I actually physically arrange them kind of within this 3D space of the package, right? I don't want to 3D stack things if I don't need to, just because there's expense and power and thermals and other challenges to that. On the other hand, I might want to because if I need a high amount of communication between those components, and that's advantageous. But there's also other aspects of it where it's just like I have to stack them because I have no more room to put anything else, right? Where I've kind of grown as far as I can, and now I have no choice but to go vertical. And so this is again a very difficult just optimization problem, and I think a lot of the there could be interesting opportunities of applying machine learning or other techniques to help explore and whittle that space down, so that given objectives, we can at least have a starting point of reasonable overall SoC architectures. Mentioned power. Power is obviously a big problem even today, right? But power, comes in multiple different flavors of challenges, right? There's that first kind of the long haul power delivery of how do I even get the power into this package, right? And as I cram more and more components in there, I'm going to likely consume more and more power. There's things you could do, like there's dark silicon and things of that sort, but like we really don't like dark silicon, right? Because dark silicon is basically silicon you're paying for and not getting value out of, right? If I have silicon, I've paid all that money for it, I want it to be computing something for me, right? So, dark silicon is something we kind of have to live with, but it's not really truly desirable. Right, and then once you get the power into the package, right, that last mile is also often very challenging, right? And there's actually additional, really interesting things like, do we integrate more voltage regulators, or be able to do step down of voltage, right? In the same way that we have power brought in on the high tension lines at very high voltages and such, right? Then we get them. We have substations that then step down the voltages, and even often within the building you may have 240 volts or 120 volts and things of that sort. And there's a lot of infrastructure that goes into that that delivery of that power in that kind of that last mile, right, or the last feet in perhaps. Likewise, we have to think about that. We've got all of these different chips. How do we actually get the power to all the right places in the right amounts with the right allocations and such, right? Again, I don't have a good specific answer for that. It's also going to depend quite a bit on your specific design, your specific architecture, right? Do we have to do that kind of manually every time for a given set of chips? Is there some automation to help that? Is there a more generalized methodology or theory for doing that? I don't know. But it's just, I think, going to continue to get more challenging, right? At least like, in the US, everything's, for the most part, 120 volts, right? If you look inside a processor, there's some things, there's many different voltage rails, right? Your cores run at one voltage, the caches run at another voltage, the memory interfaces run another voltage, IO runs another voltage, right? So, if you had to build this building and bring in like 16 different, levels of, 120 volts and 150 volts, and, I guess you make a lot of money as an electrician. Right. And then this gets even more challenging as we go to 3D, right? Because you bring the power in and the power gets delivered from the bottom. But as we want to get more aggressive and stack more things together, and again, it might not be because we want to, we may not have any choice but to start stacking things to hit our objectives. Now we have higher IR drops as I'm stacking, as I'm just going more and more layers of metal. It just becomes more resistance on that power delivery, right? The inductance adds up, so there is these simultaneous switching noise effects, DIDT types of challenges. And I've also just simply got more components which can have potentially a wider range of dynamic behaviors, right? I have to worry about this thing switching when that thing's not switching, or if these all switch at the same time, or things close by switch. And I mean, there's just more cases, more scenarios one has to worry about, right? Kind of in the building analogy, a lot of if you do the undergraduate circuits, classes, right? You often use the water flow analogies for current, right? And then if everyone flushes the toilet at the same time, right? The water pressure drops, and someone doesn't have water pressure in the shower anymore, and they get burnt because all the cold water has gone to the toilets or whatever, right? And you basically have these types of problems in the chips, right? And the more stuff you pack together, right, the more likely that you're going to have these bad effects where it's not like everyone's trying to flush the toilets at the same time, but it happens. It actually happens a lot in processors because there's clocks, right? When the clock goes, it says everyone go, right? And it just becomes that much more challenging when you have that much more stuff crammed into that same area, right? Because you're delivering the power all pretty much from the bottom. And there's some interesting research on the manufacturing side of like backside power delivery and things. But even in the limit, if I can deliver both from the bottom and the top, like it's still only 2 surfaces versus however many layers I have in between, right? So this gets increasingly challenging. Power in, heat out. Right, so this is a problem again for buildings. We have all kinds, people, tons of expense in HVAC systems and everything else, right? And the problem is that you consume too much power, it's going to get hot, and that all has to be removed out of that system, for a large variety of reasons. And so we're going to start seeing, I think, and we are already seeing kind of these like urban heat island effect, issues with the processors, right? If you look at the thermal map on a processor, there's certain parts where they're really a lot hotter than other components. Sometimes it's dynamic, sometimes it's just kind of pathological. But that creates a lot of challenges, right? Because if one part gets too hot, eventually you're going to have to throttle the clock back, lower the voltage or something, which is lost performance, right? And part of this is trying to put things together so you get more performance. So how to do that? I don't know all the answers. So it's very challenging. There's another area where there's, I think, lots of co-design opportunities, both down into materials, advanced cooling techniques, and things of that sort, as well as going up. Are there things we can do in terms of job scheduling, algorithmically changing things around so that you're doing things more efficiently, or perhaps doing things in a more spatially distributed fashion, so you're not clustering all the activity. I think there's a lot of interesting questions one can think about of how to co-optimize this across the layers. There's also kind of the simple things to do, right? Like what we did for the 3D stacked cache is that we just kind of planned for it ahead of time. It's like, okay, we know the cores are hot, so we're not going to stack anything on top of it. Right, and the caches are pretty much more uniform, in terms of power density. So we'll stack cache on top of a cache, and what we basically did was just put some dummy silicon on top of the cores to help vent the heat. Right, and so there's some things you could do, like this kind of a simplistic thing, but every little bit is going to help when we start putting more and more stuff together. Right, and so in some cases there's just general kind of floor planning or whatever the 3D equivalent of floor planning is that needs to be done in a thermally mindful fashion. Right. And this also works, with the power delivery, right? Because if you have to deliver power, if you deliver too much power in one spot, you'll also have challenges. So it kind of goes hand in hand. Right. And then, but just kind of overall, we have to just start thinking, architecturally, like the thermals, and this just has to go into your planning of how do we actually, make all this stuff, work, function while maintaining reasonable temperatures and such, right? And so in the same way, we kind of waste some space in some sense in our city planning to have these things called parks and whatnot. They actually do help with the cooling and the temperature of the city and kind of mitigating these urban heat island effects. We may kind of have to start planning the kind of the thermal equivalents within our silicon structures too. All right, but it's a little bit less desirable, right? Because it's that's like prime real estate, right? A couple other things to think about. As we integrate stuff together, right, there's a lot of challenges that each of these components you need to test ahead of time, right? It's like, before you buy a house, you typically do inspection, or at least you used to before it became so competitive to buy a house. And it's the same thing, here. Like we actually have to do, some amount of inspection of all these parts before you put them together, because there's this corresponding challenge. There's this concept called a FRU, which is the field replaceable unit, right? If something breaks, what is it you're replacing, right? So today, if a memory chip dies, like a DIMM dies, it's okay, that's fine. This one chip dies, I throw away the DIMM, right? It's not too expensive, but I'm actually throwing away N-1 additional chips that might actually still be working, right? But that's not so bad. But now when I've actually integrated all this stuff into this package, I've got all these accelerators, all this expensive silicon, multiple stacks of memory, and all kinds of things together, and like one little thing dies, do I have to throw that whole thing away? Right? Like, so, that's basically like, having a building where like the escalator dies, and then I decide, okay, I'm just going to demolish the whole building, right? But that's basically like, what is going to happen, right? That's kind of like, what already happens with, a lot of our components. Like, we don't know why, like, the chip died, right? Maybe just like a connection failed or whatever, but you just throw the whole thing away. Right? Even worse, you have to throw like the whole laptop away or something like that. That's horribly expensive. Right, and so we have to start thinking about, how do we actually design for greater resiliency? How do we design for things that they can just, fail in place, right? Because I can't go in there and replace these types of, components that are, 3D integrated or whatever, right? So again, this is something where I think there's a lot of opportunities going across a stack of, could be algorithmically, are there, different ways to structure the problem, the computation to be more tolerant in some fashion? Are there, other things to do across the different layers that make it so that I don't have to do something so wasteful, right? Another area that I think is going to a lot of interesting opportunities is kind of the whole parallel of smart cities, right? Like a lot of people talk about smart cities, and we've got all these sensors and all this data, and there's a lot of different things we can optimize about how we run the cities. Kind of classic examples like traffic-related things, that type of sort. In our processors today, already we have thousands of sensors throughout for monitoring things like the power supply, voltage levels, noise, thermals, and whatnot, right? And the control system for these are still relatively on the simpler side. We have different kind of microcontrollers, different control algorithms for reacting and monitoring things. Right, but I think there's, we get to the level of like thousands of sensors. I think there's really cool opportunities of, how do we build, more intelligent, more robust systems to really, optimize how we're, running these things, right? So, I think that's a really interesting point. And I know I'm kind of running a little bit long, so I'll quickly run through. I'm not going to go through this in detail, right? But there's a lot of, additional things to think about, like budgeting. It's simply like power, right? There's only so much power to be spent. How do you decide what goes where, right? There's, typically if you actually light up everything on a chip, it's going to way exceed your power budget, right? So how do you actually do that in a way that, maximizes the value, the performance, whatever, of your application? Security issues. In real life, the analogy is security in hardware, right? There's going to be you're plugging all these things together, just a multitude of security things that we have to think about, things we perhaps haven't even thought about, new attack vectors and such. You're not going to go into detail there, but, certainly something to think about. Interesting things to think about in terms of policies. There's going to be things for quality of service and fairness, how all these different things are interacting. You need to have some convention, some ways to make sure that the system behaves in some expected or predictable fashion. And in kind of language, you got all these components working together. You need common protocols, and some of this may not be rocket science to define, but someone has to go and figure out what is a way that all these things are going to interact in a sensible fashion, right? That's both things like point-to-point communications, or things like test and boot up reset protocols. There's all manner of things that just have to be worked out for the things to really play together correctly. All right, and then kind of the last big topic. Kind of the analogy here is that, on top of all of these architectures, everything else, like something has to be done, right? And that's basically the software, right? So there's a ton of work, that needs to be done to think about, whether it's the runtimes, operating systems, libraries, firmware, all the way up to the applications and algorithms. Depending on what kind of architecture you come up with, that's going to have all kinds of implications on what the software does or doesn't have to do. Right? Ideally, we don't want to affect the software, but likely there is going to be, some things that are necessary, some things that are opportunities. So, too much to really kind of cover there. So I'm going to kind of skip the last couple just because we're kind of running out of time here. But there's things that just kind of go beyond the socket. You start thinking about how different components start interacting together, right? So it's kind of pairwise cities, or things like photonic interconnects may actually now start thinking of as like the lines start blurring, because you can start really thinking about how all these components are working together. So if you want to talk to me afterwards, we can talk about that some more. So hopefully, this kind of this again, this is like far more questions. I basically have no answers for most of this, right? But there's, I think, just I'm personally very excited because there's so many new research opportunities, so many problems to tackle here across everything from classical CS all the way down to hardcore electrical engineering and all types of interactions in between. Right, it's like the research opportunities are incredibly rich. I think there's a lot of cool stuff, and I think aligns really well with a lot of the research that's already going on and being advocated by the folks here. So with that, I'll wrap it up.
Thank you so much. Question for Gabe. I think we have this thing and this all around. Thanks.
So I have a question about the first part where you were showing the partitioning of the chips from a monolithic big size chip. So when you partition, you do give up the communication, right? Because for the monolithic thing, you could communicate at will, but now you will have some constraint in how. So how much is that a problem, or is it a problem at all, or how does that get resolved?
Sure. So part of part of the challenge, right, is figuring out we can cut things wherever you want. Where does it make sense to cut, right? And so fundamentally, you do have to figure out for a given integration technology how much bandwidth can be achieved, right? So for our first generation stuff, we're doing everything over kind of standard organic substrates, which have some limit on the bandwidth. If you do things like silicon interposer, these 2.5D or even 3D, then you have higher levels of bandwidth. All right, so then you basically have to do that matchup, right? For where do I want to cut, how much bandwidth is required, and then what kind of technology is required to support that, right? Or you work the other way around. Like for example, for those parts, it would not have been economical to use anything really but the organic substrate. So we had to figure out, given that constraint, what kind of bandwidth can we achieve, and then where does it make sense to cut it, right? Should we have because in this case, it was kind of natural in that we have our, in particular for like the second generation with the cores and the I/O die, it was a very natural partitioning, and we can figure for a certain number of cores, I need this much bandwidth, and kind of work backwards, and you can figure out. That also drives things like, should I build a larger number of smaller chiplets with because I can have fewer cores, but perhaps that way more bandwidth per core. Or should I build like a smaller number of larger chips, right? And there is some balancing, but largely it's just kind of driven by the architecture, targets and constraints, and the technology constraints, and to figure out and really what makes sense, what achieves your results.
Okay, great. We actually have a discussion right after this, and we're already 10 past the hour. So Gabe will still be around after the talk. So if any of you have any questions, feel free to talk to Gabe. But with that, thank you so much, Gabe, for the wonderful talk.
Okay.